Hi BC Calc, happy spring break. It's Tuesday. We're going to start our screencast series right now. I don't think any of you have been looking for it, but if you have, I'm sorry. Instead of starting McLaurin and Taylor series, I've decided that I'm going to just mop up some various little things, and hopefully those topics will be clear. So we're going to start by looking at polar again a little bit. So some of this is going to be review. Some of it, you probably could have reasoned out, but might be sort of new. And there'll be an example problem and then maybe some homework after. All right, so suppose we were going to graph something. And if my kids come in, it's a theta. If my kids come in, I apologize. Let's say that we were going to look at this graph, and I asked you to graph it. And periodically throughout these videos, I'm going to tell you to pause me and try it on your own so that we can sort of assess where you guys are at, as you move forward. Okay, so you should be able to graph this. This was something that you were assessed on, okay? And so pause me and try it. Okay, so hopefully you have something that looks pretty good. Right, remember we said that we would start with our four angles here, right? Because this thing's gonna have a period of 2 pi. So we'd start with these four angles, and we'd plug in some values, right? So if theta is 0, r turns out to be 6. If theta is pi over 2, r is just 2. If theta is pi, r is negative 2, and if theta is 3 pi over 2, r is 2, right? So some things to think about, right? We do see that r changes from positive to negative, right? And again, that's because this a here is bigger than this b, right? A cosine theta plus b, or a sine theta plus b. If a is bigger than b, right, we're going to end up with one of those limacons with that inner loop, okay? So let's graph these 4 points and remember how we sort of went about it, right? So 0, 6, that's out here. Remember, we made a little 1. Pi over 2, 2. It's maybe here. Pi comma negative 2. Remember, this is in the pi direction, but negative 2. So that's right here. And then lastly, 3 pi over 2 comma 2 is down here, right? Okay, remember, we always sort of moved in this counterclockwise fashion, right? Because we're tracing out these angles, right? And so we're going from 1 to 2, so that looks something like this, right? Because remember, if you think about what dr d theta is in this here, right? Dr d theta, the derivative, how fast r is changing as theta changes, well, that's just negative 4 sine theta, right? Which is negative here and getting more so, right? It's negative and getting more so in this quadrant, right? And it's still negative in the next little bit. Okay, so now we're going to go from 2 to 3, and we're going to have to sort of go through this origin. And let's pause quickly and say, okay, in between here and here, we must have hit 0. So if we say when is r equal to 0, right? That's solving this equation, which hopefully you solved. And if you didn't, you should pause me again and figure out, right? This is negative 1/2 equals cosine theta, or theta equals, right? And then we got to use our unit circle knowledge, right? This is going to be 2 pi over 3 and 4 pi over 3, right? So that's going to come through here and then out the other side. Why does it come out the other side? Because remember, we're tracing out these angles in quadrant 2 over here. Should have used a different color for that. We're tracing out, these angles in this realm, right? And so part of those, r is negative, and we're going to come into this inner loop right here, right? And then we got to go from 3 to 4, and that's sort of the exact opposite. So here we're at pi, and we're going to go up to 4 pi over 3, and that's the other half of this inner loop. And then this little piece down here. Think about it now also. This derivative is now positive. It's now positive, so we should be getting farther and farther from the origin. And then 4 to 1 is kind of easy, right? That's just going to keep on coming out in this nice round fashion like this. Okay, so hopefully you were able to come up with something like that. If not, I encourage you to look back and sort of review some stuff. We'll have plenty of practice coming up. Okay, so now let's recall, how did we find the volume in polar coordinates? Let's find the volume of this inner loop. Okay, so recall, right, with regular in rectangular coordinates. In rectangular coordinates, right, if I had some curve up here, right, we summed these little rectangles from A to B. We looked at all these little rectangles, and we looked at the height here, and we said, okay, find this f of x, that's the height, and then this dx gives me some thickness, right? And so the integral, the area was just the integral of f of x dx from, A to B or whatever. Okay, well, similarly, in polar coordinates, suppose I have some curve. My pen wasn't working. In polar coordinates, right, if I have some curve out here, and that curve wasn't very interesting. Who knows? Okay, maybe like that. And we were trying to find the area swept out from A to B. Those are angles now. Right? Instead of looking at sort of rectangles, we looked at these little sectors, right? Where we looked at this little sector here, and I said, oh, I know this length is r of theta. How much area did we sweep out, right? And this angle in here was d theta. And the answer, of course, was, remember the area of the whole is pi r squared, right? If we thought of these things like circles, just like we think of these things like rectangles, the whole is pi r squared, and then the fraction is pi r squared times d theta, the angle, over the whole 2 pi, right? Which you guys can see simplifies to 1/2 r squared d theta, right? So remember, this integral was the integral from A to B, where those are now angles. Theta equals A to B of 1/2, that sort of came out, and I had r squared d theta on the inside. Okay, so to find the area of the inner loop, the hardest thing you're going to end up doing in polar coordinates is to think about sort of what my limits are, right? Where does this loop start and where does it end? Fortunately for us, we've done that already up here. We said 2 pi over 3 and 4 pi over 3. Right, so if I'm trying to find the area of this inner loop, we're going to go from 2 pi over 3 to 4 pi over 3. So this area of inner loop, right, is going to be the integral from 2 pi over 3 to 4 pi over 3. And then what goes in there? Right, well, there's a 1/2 that comes out. And then what goes in on the inside? R squared d theta. And what is r squared here? R squared is simply this 4 cosine theta plus 2. That's what r was, right? That's what the original r was, squared d theta. I'm not going to ask us to actually evaluate this. Evaluating 4 cosine squared theta requires you to use a double angle formula that can be a little messy for some of you. Okay, so that's how we find this. Okay, let's move on to a different example. Hopefully that made sense, that this thing right here represents the area of my inner loop. Okay, so moving on, let's suppose that I gave you these two curves and I asked you to graph them. So here's another instance where I'm going to say pause me and graph these two things on the same set of axes. Okay, hopefully you guys came up with something. R equals 2, that one's kind of easy. We'll do that one in green here. R equals 2, well, that's just a circle with radius 2. I'm obviously going to do a terrible job on a live screencast of drawing a good circle, but we're doing pretty well. Oh, that wasn't so great. Oh, that was bad. Okay, that one's okay. R equals 4 cosine theta. We might not remember what this is. There's a plus 0 here if we can imagine it, right? So if you were to make one of our little charts again, what would we have, right? We'd have 4, we'd have 2, no, 0, sorry, 0, and then we'd have -4, and then we'd have 0 again, right? So this one we might actually need some intermediate points, right, to see what's going on. But if you remember, cosine theta is one of the first graphs we drew, right? It's actually a circle with radius 2. So it actually looks something like this, and its period is actually just pi because of the negative there, right? So this is actually the same circle just moved over, okay? The same circle just moved over. And let's suppose that we were concerned about finding, I don't know, which area should we find? Let's find this area. Okay, that area might be kind of scary. Okay, how would we find that area? Well, as I said before, the first thing that we're going to need to find that's kind of scary is our bounds, right? So this is clearly going to go from theta equals 0 to theta equals whatever this is, right? So we need to know this intersection point. Where does 4 cosine theta and 2, where do they intersect, right? So that's a good thing to sort of try to puzzle over. So why don't you pause me and think about where that is? Okay, so if you've thought about where that is, right, that's where these two things are equal. That's where 4 cosine theta equals 2. Or again, cosine theta equals negative or equals 1/2, right? I keep on giving myself that because it's sort of nice. And if this were like root 2/2 or something, it would have to be sort of contrived, right? So we're gonna get theta equals pi over 3 here. This line here is that ray, theta equals pi over 3, okay? And you'll agree, this problem is sort of like a top minus bottom. So again, I'm going to sort of have my rectangular coordinate analogy here on the left, and then hopefully we'll make some sense of what that should be in polar coordinates on the right. So we have a top and a bottom here, right? And remember, the area between from A to B, this area here in rectangular coordinates, or normal coordinates, whatever we want to think about, right? This was the integral from A to B of f top minus f bottom dx. And remember where that came from, right? That really came from saying A to B of f top dx minus A to B of f bottom dx, right? That was sort of where that came from. And that was because the blue area would be the same as this whole orange area minus this green area down here, okay? And we're going to have a similar thing in polar here. This pink area, right, this pink area is the whole area, which I'm going to try to highlight here, this whole area minus this little guy in here. Hopefully that's clear, right? It's the whole minus that little, right? So instead of f top minus f bottom, we're going to sort of have f far away minus f close, okay? And we're going to think about what that looks like in polar coordinates, okay? So in polar, we're going to sort of go backwards, so I kind of regret having these two lines these two lines down here not be in the opposite order. But, you know, we're going to make some mistakes while we make screencasts on the fly. So let's suppose I have some curve, who knows, it looks like this, and then I have some curve in close like this. Well, we're saying that this pink area in here is the whole thing. So all the area inside the outer curve minus this little area in here, right? And that should make sense. So what that looks like is to say, I guess I don't have any limits, but you guys get the picture, right? From A to B, F far really don't mean F far. I mean R far. R far squared d theta. So remember, that's the whole area. That's the orange shaded area. R far squared d theta. Remember, back from up here with 1/2 R squared d theta. Minus 1/2 integral from A to B of R near squared d theta. Right? So then you could combine them, right? So again, I regret this other, just pretend these guys were swapped, right? We could combine them into 1/2 integral from theta equals A to B of R far squared minus R near squared d theta. And notice, just like with our washers in when we were revolving things around, this is not R far minus R near squared. It is R far squared minus R near squared. Okay? So, coming back up, right? Coming back up, if we were to actually express this area as an integral, right? This area is going to be the integral from theta equals 0 to pi over 3. 1/2 comes out. R far squared, that's the farther away curve, 4 cosine theta squared minus R near squared, 2 squared d theta. Okay, hopefully that made sense. That's sort of how we find these these areas. Okay, I want to talk about one more thing, and then the screencast will come to an end. Okay, so let's go back to our original friend here, 4 cosine theta plus 2. And maybe I'll just work off to the side. That's gonna bother some of you. So I have R of theta equals 4 cosine theta plus 2. That was right? Okay. And this thing, again, right? We had this thing out at 6. That was the 1. We had a 2. We had a 3. We had a 4. I probably should have just copied this, but you know, it's good practice to draw these things as many times as possible. We have this curve that comes swooping in here. That's not the roundest, prettiest thing we've ever seen, but you guys get the picture. Plus, we've already drawn this. Okay, so we talked about, and the AP loves talking about, the slope of the tangent line to this curve, right? And you say, how do I find a slope when I have theta and r? Well, we can find dy dx, right? This is always the slope of the tangent line at a point, right? We can always find that. So let's suppose we wanted to find the slope of the tangent line, I don't know, we'll say here, right? This point here, which remember was, what was that? That was 2 comma pi over 2, I think. That's what that point was. So if I wanted to find the slope there, well, how did I find that? Well, to say dy dx, remember, we said this was equal to dy d theta over dx d theta, right? And the theta sort of cancel with our hand wavy math, right? And dy d theta, how could we find that? Well, y, we remember, is r sine theta, right? So this is really just taking the derivative of r sine theta with respect to theta. And what is r? R is this thing. So y is actually 4 cosine theta plus 2 times sine theta. Okay? And you're just looking for y prime at that point. So what would that be? Well, that would require the product rule, you say. So dy d theta, if this is what y is going to be what? It's going to be negative 4 sine theta times sine theta plus 4 cosine theta plus 2 times cosine theta. Well, that's awful, but this is a plus 2. Okay? That's awful, but that's what it is, right? And then dx d theta, similarly, is our cos theta. So that would be 4 cosine theta plus 2 times cosine theta. So dx d theta is going to be equal to what? That's going to be derivative of this guy, which is negative 4 sine theta times cosine theta. And then this guy, which is 4 cos theta plus 2 times derivative of cosine negative sine theta. Okay, so coming back here, right? If we wanted to find dy dx at a specific spot, right? What specific spot did we say? We said at, I don't remember, theta equals pi over 2. Right. This thing would be these massive fractions. So it would be negative 4 sine pi over 2 times sine pi over 2 plus 4 cosine pi over 2 plus 2 times cosine pi over 2. All over, that's this guy right here, all over this guy down here. What is that? Negative 4 sine pi over 2 times cosine pi over 2 plus 4 cosine pi over 2 plus 2 times negative sine pi over 2. Well, that's very pleasant. I'm sure you guys are very eager to figure out what that is. But that's the slope here. Sine pi over 2, well, that's just 1. And cosine pi over 2, that's 0. So fortunately, we give ourselves an easy one here. So what is that? That's negative 4 on the top. These guys are both 1. Plus 2 times 0. So just negative 4. And on the bottom, that first term 0. 0 plus, and the second term is 4 cosine pi over 2. That's just 0. So 2 times negative sine pi over 2. Negative 1. Negative 1. So that would give me a slope of 2. A slope of 2, which looks, plausible from my drawing. It's certainly positive. That's good enough. All right. So for your first homework assignment, I'm going to ask that you not look at the answers. Maybe I'll move this. I think we may have done this problem already, but we're going to try to do it again. This is an XAP problem. It is fairly ugly, but I think you guys can do it. I believe in you. Hope you enjoyed this screencast. There will be more.